All right, thank you everyone for coming. My name is Niklas. I'm a co-founder of LabDAO, physician scientist. And I'm going to be speaking about how we're going to use Bacalhau for parallelised computational biology applications. So in 2021, we set out to run a real-world experiment and say, okay, what would it look like if we were to build a scientific organization that lived completely online? And the reason why we're motivated to do that was because we believed that if we did embrace Web3 standards, we could actually improve the state of science. And I think just in the talk before, you were able to learn about some of the underlying ideas why that matters. And I think we can all summarize them in basically 3 points. First one is content addressing. Now everything is citable, so you don't have link rot. You can directly address the data that you're referring to when you're, for example, publishing, and that publication itself is also content addressed. But not only that, you are able to also have reproducible transformation over this content addressable data. So Bacalhau is just a case in point. And then last but not least, and this is really where we started out with, is the idea of like tokens, the idea that you can have co-ownership about your data the same way that people are collecting PFP NFTs, scientists could be minting NFTs, and philanthropists could be supporting them and build community around scientific discoveries. And the way that we're supporting that effort of like integrating these technologies into the way that scientists do their work is to build a laboratory exchange. The idea that scientists can collaborate over distance, they can share scientific compute on a public network, that's where Bacalhau comes in, but they can also collaborate on physical life science services, where someone has an idea and a plan, and someone else has the capacity to hand out, and there's an open source platform where they can trade those services. And eventually, that exchange has built in abilities to actually capture those inventions and mint these as tokens that serve as sort of forms of copyright protection. Now, to motivate, why does this matter? I've recently found this tweet online, and maybe just glance at the screen for the slides for one moment, and maybe someone can tell me what they think is going on here. Who has like worked in a life science laboratory before? All right, so David, what is this thing on the like side that looks like the roller thing? All right, let's find out together. So this is a research lab based in Germany, so they're pretty well funded actually. And they are running a Google Colab notebook, and because Google Colab notebooks time out after a certain while, they put the computer mouse on like the roller that they use for the Western blot machines to keep the mouse running so the screen doesn't time out. And that's like the way that people like share these types of like scientific breakthroughs like Colab fold in this particular case, which is a protein folding algorithm. And I think it's pretty easy to agree on that we could probably do a better job at doing this than having that. And really, the core layer here is that people use these Google Colab notebooks to share the tool. Like, the scientists didn't really care about how this thing was running. It was just, they just received this link, and they wanted to have, like, put in their sequence of interest and run the tool and have that work for them. And that's something that Bacalhau currently doesn't do. Bacalhau helps you run containers, but it doesn't help you get an overview about available scientific tools and what their expected inputs are. So we built a tool that is called PLEX, which is the lab exchange, and it's a Go CLI that enables you to access community-contributed container images and recommended configurations for them. It then runs them on Bacalhau, and your scientific input and output are published via IPFS. That's nothing new. Now, you can install PLEX just on your client. We're basically just giving it some configurations now, and then in a moment you can see how you run it. You basically define a tool, and then you define input data. So here, for example, we're running the tool that's called Equibind, which is referring to a container that has certain expectations about the inputs and the output format. We're giving it a directory. It automatically looks for the inputs, publishes those to IPFS, runs the container, and gets the data back. Now, what you can also see here is actually it's running 2 Bacalhau jobs because it found two, for example, molecules or 2 types of files, and it automatically scheduled that those should be 2 independent Bacalhau runs. And the way that we think scientists will eventually interact with Bacalhau and just generally in their day-to-day life is that you will have users that, for example, run Jupyter notebooks, They will connect to a Bacalhau node. They will not run it themselves on their box, and they will also connect to an IPFS node to like store their data. For example, that could be a laboratory node. Like the lab has one node that they run, where they, for example, have a Jupyter lab, a Bacalhau node, an IPFS node. And what we're interested in is like making that as easy as possible to bundle together and give to scientists, where we can tell them, hey, here's your Jupyter lab, and by the way, everything you do here is tracked. And you can easily, by sharing some of your uptime with others, you can run pretty ridiculously large compute jobs too. And then I think the power users eventually might migrate to like a cluster, such as a Jupyter Hub, IPFS clusters, and eventually also Bacalhau clusters. Now, where we came in was, again, at this tool layer. So you have Bacalhau, IPFS, and then, however, there's this like missing app store for scientific applications. And scientists, again, they want to share the tool. So, however, this is not a problem that we're solving for the first time. There have been other attempts of tracking scientific tools and making them easy to orchestrate. And one example is the Common Workflow Language. And the Common Workflow Language, or CWL, has two components. One is a tool configuration component that's defined once, and another component that's an input-output dictionary that's created fresh for every time you run it. And the most beautiful thing about it, it's only JSON. So you define one JSON object that represents the tool, and one JSON object that defines the input, tool, output triplet. Now, this is, for example, one tool or one way that you can think about it. This is the tool that was just shown in this Google Colab notebook. So on the left side, you have a protein sequence. There's some function that's called fold, and at the outside, you have the protein structure. Now, the design philosophy that we take is one that I think you might have seen before in like category theory, where scientific applications can be absurdly complex, right? There can be all these intermediate steps, but really what we all care about is, okay, what needs to go in and what needs to go out? And we just need to define what goes in and what goes out. And this is how this looks like. So it's one JSON object where you say, oh, it's a class command line tool. We call it Colab fold. This is the Docker command. This is the Docker image. These are the inputs. These are the outputs. And we basically start soft typing those inputs and outputs by saying every file that has a FASTA file ending, for example, we consider that a sequence. And every file that has, for example, a PDB at the ending, we consider that a protein. And I think this is just an invitation to like a future, hopefully, in computational biology where we'll build way more structured typers, where people will say, okay, this is a proper protein that it can now interoperate and click into all the other tools that scientists are publishing. Now, so far, we have about like 10 tools that have been maintained by the community, and we're excited to see a growth of that. However, what already is the case is that the combinatorial space is already pretty large, so you can run about 100 different computational workflows right now, 100 different experiments, and obviously on all different kinds of input data. What's also a nice second-order effect of that is that you can now click these things together. Like this is one example where we have one team that generates sequences using a large language model and then pipes them into a folding model. And again, that team is really interested in a biological problem. They're not computational per se, and such a simple abstraction over the individual tool where they just need to know, okay, what are the inputs and output types allows them to plug these things together relatively seamlessly. Now, this was a dive into the way that you configure tools. Now, how do you structure that input-output dictionary? This is one example, and we basically, again, stuck very close to the Common Workflow Language. However, with one slight modification where we now accepting the case that a file might have various addresses because it lives in different categories. There's a local file path, but the file also lives on IPFS or might live on Arweave or some other system in the future, and the way that we're defining these inputs and outputs respects that. Now, this sounds hopefully interesting, but can you actually use it for something that's even more interesting? And our answer is yes. So we were really interested in protein small molecule docking, and this goes back to, I think, a talk that you just saw a while ago. Again, also where the folks at Gridcoin, they also discovered that scientific computing, especially in the realm of molecular docking, is really an interesting use case for decentralized compute. So the problem that you have in molecular docking is that you have a protein, which is, for example, related to a disease, and you're trying to find a small molecule drug-like particle that binds that protein in a desirable conformation. And here, in this example, you can see 3 different small molecules, one in black, one in brown, one in green. And one of these is actually the predicted, the ground truth, the green one, and all the other two, they have actually been predicted, which is, I think, just an example for how good these models have gotten over the time. But still, there's some room for improvement. So we set out and said, OK, well, we should probably have some kind of benchmarking system available that is undisputable and open source. So we went ahead and we basically started to dock it on scale on Bacalhau. And in the process of that, I think we ran about like 1,500 Bacalhau jobs at times with concurrency where we dispatched 200 tickets on our private Bacalhau requester node that we set up and the nodes that attach to it. And now these are, I think, one of the first scientific slides that have been generated on top of Bacalhau that are completely reproducible, where we're now just benchmarking these two docking systems, and we see, in fact, we're able to reproduce the numbers from that paper, and we could now share with you the whole computational graph of like how we went from input data to output data, and can track all of these steps also by content address. But we can't even go beyond just reproducing papers. We can figure out new stuff too. So in this particular example, we then combined the docking system with a dedicated scoring function that was relatively recent, and we were able to show that if these pretty new docking systems, they actually reach state-of-the-art sort of experimental data pretty comparably, where you basically compare the predicted binding affinity on the x-axis, on the y-axis, the observed binding affinity. And these tools are getting ridiculously good if you compare them actually to the experimental information. And we're not the only ones that are getting excited about this. So this is a legit publication that came out of some of that work that was published earlier this year. And this is one of the authors at MIT that was sort of referring to that publication being out. And yeah, that was in part made possible through Bacalhau. And we're really excited about where this can all go for open science. Now, what's next? Well, what we want to do next is we want to create on-chain receipts of these types of transactions. So when you dock a small molecule or when you design a new protein binder, we want you to keep receipts of that. And actually, not only you should keep receipts of that, everybody in the world should know that you did that and should be able to give you credit for it. And monkey pictures are not very popular right now, but maybe this is actually a useful use case for non-fungible tokens where you collect these receipts where you can clearly show, OK, I came up with that, or I ran that experiment. What else we're going to do is we're going to run more examples. And just today, actually, there's one scientist out of Seattle that is using one tool that we've onboarded to dock a small molecule that's related to congenital disease or a rare disease related to like a bone condition, and just shared me that screenshot while I was preparing the slides. So this is happening right now, and we're excited in the next coming weeks we're going to be hopefully sharing some more of this. And then the last point that we're really interested in is simplifying the user experience. So right now you're doing all of this through a command line, and we're trying to get it easier so that there are Python bindings, that you can actually monitor the state of the queue, that you can interrupt, retry, and so on. Now, how can you help us if you're interested? Well, if you're interested in compute over data infrastructure, help us make Bacalhau or whatever compute over data framework that you're interested in or working on more compatible for life scientists, more friendly. And if you're a scientist, you can definitely do us a huge favor and tell us about your favorite application that you would like to see containerized in this community-maintained artifact registry. And with that, I'm going to say thank you. This is not just me. This is a whole community of scientists and engineers that are coming together and are trying to change the way that we publish science and we track contributions. Thank you.